In this video, I'd like to talk about all the other fractal Julius sets. So here we go. The setup is that we have our quadratic z squared plus c, and Julius set is defined as the boundary of base integral attraction to infinity, where a infinity, what I mean by that is any complex number z such that iterates of f blow up to infinity as n goes to infinity. Okay, so it turns out that it's a little bit easier to compute filled in Julius set. So filled in Julius set is the, so instead of j of f, I'm going to write k of f. These are all the z values such that the iterates are bounded, right? So everything that's not in the base of attraction to infinity. So that includes the Julius set, but it actually also includes some other parts of Fatou set. But it's the outline, the boundary is still the same as the Julius set. So being able to picture this is good. So for example, let's look at z squared minus 1. So what would be the filled in Julius set here? Well, what we could do is we could just try some z's and see if it blows up or not, right? So here are different types of things that could happen. So if we start with z equals to 0, 0 squared minus 1 is -1. And if I plug that back in, -1 squared minus 1 is 0. And if you return to itself, then it's going to repeat after that. So it's going to be -1, 0, -1, 0, and so on. So when you get something like this, it's called the periodic orbit. It just repeats. And this for sure is in the filled-in Julius set because it's not blowing up to infinity. Okay. Other things that could happen. So if you start at 1, 1 squared minus 1 is 0, but we've already had this before. If I plug 0 back in, I get -1, 0, -1, and so on. So this isn't like a z equals 1 is not a periodic point, but it's what's called a pre-periodic point. So it starts with 1, and it gets into periodic orbit eventually. But the starting point itself is not in the period. The period is between 0 and -1, flipping back and forth. Okay, other things could happen. So for this function, this particular number, 1 plus square root of 5 over 2, if we plug that in, we first square it and then subtract 1. So if you FOIL out the 1 plus square root of 5, that's what we get. And then if you subtract 1 or subtract 4 divided by 4, we get 2 plus 2 root 5 over 4, or if you reduce that, we get 1 plus square root of 5 over 2. This is exactly where we started. So instead of calling this like a periodic point, because this is period of 1, we usually call that the fixed point of f. When you plug it back in, you just get the same thing out. Okay. And of course, there are other orbits that does not repeat. Here's one, -2. If you plug in -2, so -2 squared is 4 minus 1 is equal to 3. If you plug in 3, 3 squared is 9 minus 1 is 8. And then 63 and so on. So this appears to blow up off to infinity. So we would say that -2 is in the base of attraction for infinity. If you plug in I squared minus 1 is -2, and well, after that, it's gonna do what that thing does. So I is also in the A infinity. Okay. it turns out that there are other what's called chaotic orbits where it doesn't quite repeat but jumps around. But that could happen as well. So we know some things are in the Fielding-Julius set, but how do we know for sure that these things are actually going off to infinity? So it looks like it's going to infinity. Of course, if you square, you're going to get a much larger number. And if you're subtracting 1 each time, that doesn't, of course, scoring is going to be something that's going to make it bigger, quicker. So we need a theorem to kind of take care of this case, like things that are getting larger and larger. When we're actually computing this on a machine, we can't, there's no button that we can press to ask a computer to compute the limit. So here's a way to handle the things going off to infinity. Here's a theorem. So if you have a quadratic z squared plus c, and this particular radius that depends on c, so note that the modulus of c appears there. And let's pick a starting point z naught. If for some iterate number n, the modulus is bigger than r, then that's point of no return. Like after that point, it's going to be approaching infinity. So we're going to prove this, but if you look at the radius r here, this might give you a hint on how you might prove this, right? If you looked at that and thought maybe that kind of looks like quadratic formula, that's exactly where it came from. So I think I'd like to start the proof not by knowing this complicated formula, but how you might arrive at the radius where this works. So we'll try to prove it on our own without knowing the answer first, and also use the reverse triangle inequality. So basically, what I want to say is that the n plus first iterate, the modulus is going to be larger than it was for the nth step, right? We're going to show that the modulus has to increase. Therefore, it doesn't, there's no point of, it's past the point of no return. Okay. So, well, that is Fn of z naught squared plus c. That's plugging in the nth iterate into the function f. And because we have a hint, use reverse triangle inequality, and we have a modulus with two terms inside of it. Let's apply it. Okay. So the reverse triangle inequality says that this is at least as big as this expression right here. All right. And what I want to say is that it's the n plus first step is larger than it was before. So let's say what it was before, at the nth step, it was greater than r. Right? Okay. So we have this expression, and we want to show that this expression itself is greater than r. Okay, because this is now the n plus first step, we want that to be greater than r as well. Well, what r would work here? Looking at this portion, Or if I bring the r to the other side, okay, we have an expression that's quadratic in r that we want to be bigger than 0. So what r would work here? Well, let's set it equal to 0 and figure it out. We can use a quadratic formula. So minus b, and the coefficient of our term is -1, so +1, plus or minus root a squared, sorry, b squared, which is 1 minus 4 times 1 times negative modulus of c all over 2. So if I graph this function right here, it crosses the x-axis twice, plus and minus. So this is 1/2, and it's plus or minus something from 1/2. And everything after this, if the radius is bigger than that, it will be above, it will be greater than 0. So the r radius that works is the 1 plus root 1 plus 4c all over 2. I hope that made sense. As long as r is greater than this, when you r squared minus absolute value of c is going to be greater than r itself. And that's how they got the previous formula. Okay. So these Julius sets are very complicated. There's no clean closed formula that we can write down to describe the shape. So we're going to be using computers to illustrate this. And basically, we're going to use that theorem, and this is the logic behind the computer's code. Okay. And if you know your own language, you could actually probably write this down and run the program yourself. So the first thing to do is to choose a window. So look at a complex plane, and we want to be able to picture this in a finite time. So we're going to pick the real part is between some number a and b, and imaginary part is some between c and d. Okay. We also don't want to do an infinite loop, so we're going to pick a maximum iteration number. So 1,000. And for each pixel on the screen, so you have a particular x and y coordinate that corresponds to that pixel. So like maybe pick like a box on that pixel and look at the center coordinate for that pixel. And you start computing the iterates. And you're gonna compute this number over and over, plug it into the same function, making sure that the radius is never too big, right? If it crosses this magical number radius, that's when you cut it off and say, well, this is gonna go off to infinity, so I don't have to do any more computation, right? So if the radius is exceeded, let's say we call it white, that pixel. And then otherwise, so if it stays within that radius for 1,000 iteration, then maybe there's a good chance that it'll stay bounded forever, right? So we'll leave it black. You could do something slightly fancier. If it takes lots of iteration before reaching that radius, you might do a different gradation between black and white. So if it takes longer, leave it darker. If it exits immediately, leave it whiter. And you repeat this process for each pixel on the screen. And we'll get a Julius set. So let's look at it in action. Okay. So this is a Julius generator. So we could pick points. So the algorithm that I described is the escape time algorithm. So I'm going to click that one. And basically, I'm going to pick any complex value, and it creates the Julius set on the right. Right? So that looks like that's little dust. These look like, these are called rabbits. That looks pretty. What I like is going in these armpits. You get some really cool spirals going on. You can go to a crack here. It looks like broccoli. And you can kind of see lots of different qualities of pictures that we can get. They're all very complicated and weird looking. That looks like a lightning. And if you kind of click on the white space, we tend to get dusty points. Yeah, I really like clicking on, I don't know what to call it, these cracks or armpits is what I call them. This is a very pretty picture. Okay, getting back to the notes. Let's see. Okay. Let's see. So one thing that you might have noticed is that some Julius sets are in one piece and some are disconnected. So remember, like some look dusty, like just a few points kind of scattered around. Other had like blocks of black space. That's a filled-in Julius set. And I didn't mention it, but there was a picture on the left that I was clicking on that I didn't describe what it was. What's on the left here is what's called the Mandelblot Set. Okay. This is a set of all parameters of complex numbers for which the Julius set is connected. So kind of going back to the, sorry. I want to go back to the generator. Notice that every time I click on the black portion of the Mandelblot set, I get blocks of black filled in connected Julius set. And then if I click outside of the Mandelblot set, I get these dusty, disconnected points. Right? And if you can click on some points, you get, you're barely on the Mandelblot set where it looks like lightning. If you click slightly off, then it's all disconnected. If you click it right, then you have some connect. These are all connected. So these are Julius sets. It looks amazing. And now we have the definition of the Mandelblot set as well. So Mandelblot set should be thought of as kind of a map for all Julius sets. So like this fractal itself is going to tell you which part of the Julius set is connected and which parts look all dusty, I guess, is my best descriptor for that. I hope you enjoyed this talk. We will continue this next week.